Ah, tá chamando aqui. Olá. Olá. Então,
Yo puedo compartir, pero solo Google. Mira, yo voy ahora
só no Google.
a pestaña. Solo me deja hacer lucro, pero no me deja PDF.
Deixa só o Google
Mira, yo
Ela
O PDF ela não está conseguindo.
diz para ela não minimizar o PDF. Às vezes quando minimiza...
Bojana. Alô?
mandé a
Mandou a Luísa o PDF.
Tá.
Não pode minimizar o PDF. Não pode minimizar o PDF. Deixar
Agora saiu.
a tela completa
Pode
aberta.
trocar de tela sem minimizar.
No, mira, yo pongo mi PDF ahora, pero yo no creo que ustedes lo vean.
Não, não estou vendo.
Apareceu e saiu.
Aparece, Sally.
Chegou a aparecer aqui agora.
Chegou? Tá. Se eu mandar pro WhatsApp de vocês, você consegue pegar aí?
Sim?
Sim. Então... com ela?
Quer falar aqui, ver se ela ouve?
Eu prefiro falar aqui. Você está testando.
Mas vê se ela ouve o som.
Dale. Tchau.
Bueno, hello everybody. Sorry for the delay. There were some technical problems. Now I'm not sure if you see this maximalized or not. Is it on the whole screen or not? Yeah?
Vou apresentar a voz solamente momentito.
Okay.
Ah, ok. Posso falar agora? Our speaker now is Bojana Femić. She is speaking about bicategories, two monads, enriched and internal categories. And she is from Mathematical Institute, Serbian Academy of Science and Arts.
Okay, thank you, Virginia. Hello, everybody. I'm sorry for a small delay, but okay, let's start. I don't know if you see this. I don't know how to move these things from the middle of the slide. Do you see them? Like over my name, there are some pins which I don't know how to remove. I'm sorry. Can somebody tell me if what you can see on the screen? Do you see everything? This also these videos here on the right of the people that are attending?
We just see the PDF.
Oh, great! Thank you. Thank you. Great. Yeah. So first of all, I want to tell you that today in the morning when I opened my mail, I saw a news. Well, Virginia already read you the title of my course, and I saw the news that Jean Benaboú, who introduced bicategories and whose important work I'm citing throughout the course, he has passed away on Friday. So it was important news to share with you and the sad news. So I wanted also to read you something about him that I read from this email, and I actually wanted also to show you this other file. Let me try, or okay, it's complicated. So the main reference that everybody who works with bicategories cites is Jean Benabou's paper from 1967, and it's called Introduction to Bicategories. About him, some few words about him, about Benaboú. Benaboú studied mathematics in Paris, but he was originally from Morocco. He studied with Charles Ehresmann, who I will mention in my course, but was deeply influenced by Grothendieck and his school. He is well known for his fundamental contributions to category theory. For many years, his seminar had an important role in the development and diffusion of category theory in Paris. He was a pioneer in the theory of monoidal categories, monoidal functors, and related matters. He introduced bicategories and distributors in 1977. Though he didn't write as much as some others, his work has been enormously influential. So I just wanted to share with you this note before starting the course. So now I will proceed. And how I'm going to the next slide. Sorry because this is all from the Google, so I don't know. The pages are not moving. What's happening here? Is there some technical support? I cannot move to the next page. I really don't know how to. Or here. Okay, here it moved. Okay, so here is the overview of the course. We will have 3 classes. In the first one, we are going to see these things. So I'm going to recall categories and monoidal categories, although I suppose that most of you already know what they are. Then we will define bicategories and 2 categories. We will see also functors among them and higher categories that they make. And at the end, I will mention strictification theorems. In the second class, so tomorrow, we will see double categories. They are specific internal categories. And then we will see monads and also 2 categorical monads. And for the last class, I leave internal categories in general as specific 2 categorical monads. Then enriched categories and the question when they induce internal categories. Then 2 monads in 2 particular bicategories, that of spans and matrices. You will see why they are important for us. And finally, double category of monads. And I will show you why vertical morphisms of monads are useful. Good, so this is an overview of the all 3 classes. And now let us start with today's talk. It is about categories. So as I say, I suppose that, okay, this will be known to the most of us, known, but also because of bicategories, it is good to recover the definition in 1 dimension. So a category consists of a class of objects that we denote by ob-C. Okay, then for every 2 objects, A and B from this class, there is a set which is called home set from A to B, and we denote it like that. And there are inside of this home live morphisms, which we denote, for example, by F from A to B, and they have a composition which is associative. That means that if we take 3 of them, which are mapping like this, F, G, and H, then their composition is associative in this sense. And for every object A, there is an identity morphism such that if you first take identity and then F, it is same as F, which maps from A to B. And it is the same if you first apply F and then identity on B. So, okay, this is a category, and as I say, I guess everybody here knows what they are, and let's say some examples. So the category of sets and their maps, groups and groups maps, algebras and algebra morphisms, chain complexes and their morphisms, topological spaces and continuous maps, vector spaces and k-linear maps, and modulus over some ring. These are just some examples. Now, among categories, there are functors. So from a category C to a category D, there is a functor F if the following is satisfied. So there is an assignment that to each object of the category C, this functor assigns an object in the codomain category D. Then for every fixed 2 objects A and B, there is an assignment from the home set. Observe that before I denoted it by home and now by C. I mean, both notations are usual. This C is saying that these are morphisms living in C. So to any morphism F, the functor is assigning another morphism in the category D from F of A to F of B. And most importantly, a functor needs to satisfy these 2 laws. One is the compatibility on morphisms, so it is strictly compatible with the composition of morphisms, and the other one is the identity, it preserves identity on objects, the identity morphism on objects. Now there is a 3rd level corresponding to categories, and that is that among functors there are natural transformations. A natural transformation, for example, omega, that maps from F to G among these 2 functors, well, it acts between functors which both act on from between same categories from C to D, let's say. And the natural transformation consists of a family of morphisms, so that omega, when you evaluate it at an object in C, you get a morphism in the codomain category D. So it goes from f of A to G of A. And most importantly, for every f in the domain category C, the natural transformation needs to satisfy this law. That is, that omega evaluated at A and then followed by G of f, this as a morphism should be the same as f of f and then omega of B. So this law should be satisfied to have a natural transformation. Okay, so far, I guess that everybody or most of you knew about it. And now let's go to the next gadget, and that are monoidal categories. So a category C is called monoidal if it is equipped with the following things that I will write down here. Firstly, we need to have two functors. One is like this, denoted like this, a tensor product from the Cartesian product of C to C itself. And another one is the unit functor that goes from the trivial category to C. What is the trivial category? It has one only object, which usually, you can denote it as ever you want. We usually denote it by a star, the same way as the category itself. And in this trivial category, there is the only one morphism, which is the identity on that object star. So if a functor assigns to that object some object in C, then this image object we will denote, and that's a usual notation, by I, and this I stands for unit. So it is called monoidal unit for C. Except of these two functors, we need three natural transformations, which are isomorphisms, and these are alpha for associativity, lambda and rho for left and right unit. Now, natural transformations should act between functors, combination of tensor and unit, but here I wrote immediately when these transformations are evaluated at objects, right? X, Y, Z, and so on. So here associativity doesn't hold strictly, right? But up to an isomorphism, and there is a morphism for every fixed X, Y, and Z. And now, moreover, these three natural transformations should satisfy the following two laws. One is usually called just pentagon or pentagonal diagram or a star-shaped diagram, and one triangle. In the pentagon, so observe that alpha was defined for three objects, and now this pentagon is defined for four objects. There you have a choice how to put parentheses. You have a choice of how putting these parentheses for associativity. And if you start in this vertex from most left position, you have two ways to apply alpha. So first, like alpha tensor identity this way. And then there is the only one way how to proceed, alpha like this and alpha on this right side. And we end up so that the parentheses are at the most right. And on the other way, we could have regarded these two as one object and then apply alpha here and then alpha here. So these two should be the same. And this is the pentagon, typical pentagon for monoidal structure. And in the triangle, we put this identity, the unit object, we put it in the middle, then apply alpha. Here you apply left unity constraint and here right, and this should also commute. Okay. Now some examples. Well, the first one that everybody knows is the vector spaces where the over some field k, the tensor product is over k, the unit is k itself. For a commutative ring, we have the category of R modules, actually R bimodules. So thanks to the fact that R is commutative, you can define, if you start from left R modules, you can define right action of R by acting the same way as on the left. And this is precisely thanks to the commutativity of R. In this case, the tensor product is tensor over R and the unit is R. The next example is when R is not commutative, but then we need to say that these are R bimodules, where the left and right action of R can a priori be different. Again, the tensor product is over R and the unit is R. Then for a quasi-bialgebra or a bialgebra in vector spaces, the category of modulus over B is monoidal. Well, just to have a module, you need an algebra structure, but for bialgebra, and since here the tensor product is over K and the unit is K, so the field, the monoidal structure is given precisely thanks to the coalgebra structure and the two compatibilities between algebra and coalgebra structure. Even more generally, if C is any braided monoidal category with braiding phi, it doesn't matter now if you don't know what it is, it's just an example, and B is a quasi-bialgebra or a bialgebra in this category C, and these are axioms for bialgebra, then the category of modulus over B is also monoidal. Okay, so these were examples of monoidal categories. Now we can define monoidal functors and monoidal natural transformations. There are much structures, but let's just move on. And now I would start with bicategories and two categories. So as I mentioned you at the beginning, bicategories were introduced precisely by Benaboú. I don't write it in this slide, but they were introduced in 67. Here is a definition. B is a bicategory if, well, it has the following data and axioms. At first, so there are three levels of story. The first level are zero cells or objects. So A living in the class of B, these are objects of B. Then for every two objects, there is now not a set anymore, but a category, B from A to B. So since this is a category, we have objects, which are called one cells for the bicategory, and there are morphisms, which are called two cells for the bicategory. Now, sorry, for the category itself, there are some axioms, and we will come back to them later. But let's go on. There are additional axioms, and these are that for every object, there is a one cell identity on zero cell. Is there some question? For every object, there is a one cell identity on that object. And for every three objects, A, B, C, there is a bifunctor composition. So this is a category, this is also a category, and this is Cartesian product of categories with component-wise operations. Now this bifunctor should be associative and compatible with this unit up to isomorphisms alpha, lambda, and rho, which can be formulated in terms of natural transformations. And they should satisfy a pentagon and a triangle that I show in the next slide. So here I borrowed one page, and let's see, if you take F, G, and H, three composable one cells, then alpha evaluated at these three one cells is a two cell, acting like this. And then lambda, the left unity, is acting like this, and rho, the right unity, like this. So the difference between a monoidal category and here a bicategory is that in a monoidal category, we had that these places objects, alpha, lambda, and rho were evaluated at objects, and now they are evaluated at one cells of the bicategory. And the same two axioms should hold. Here is the pentagon for alpha, where instead of objects, here we have now one cells, and the triangle with the identity in the middle and left and right unity constraints. Okay, so these are the same axioms as for monoidal category. Now, having said this similarity with monoidal category, my first example will be a monoidal category. My first example for a bicategory will come from a monoidal category. So suppose that C is a monoidal category, and let's make a big category out of it. For zero cells, I put only one zero cell, let's call it just star. And now for one cells, not only do I take identity on the star, But for every object from my monoidal category C, I just name it that it is a morphism on that unique object star. Okay, so this is different than in the trivial bicategory. And among any two one cells or objects in C, I just take for two cells to be morphisms among these objects. Now in every bicategory, I need to tell you the composition of one cells. Well, guess the operation for composition that we have on objects in a monoidal category is precisely the monoidal tensor product. And for the monoidal tensor product, we already have alpha, lambda, and rho, which are the associativity and unity constraints. And these precisely will play the role of the analogous two cells that are necessary for a bicategory. At this place, note that alpha, lambda, and rho in a monoidal category are a priori not identities. They are isomorphisms. So this same thing happens in bicategories. And actually, if alpha, lambda, and rho are identities in a monoidal category, the monoidal category is called strict. And if alpha, lambda, and rho and a bicategory are identities, the bicategory is called a two category. So this is the main difference with two categories. Okay, that's enough about this example. Let's go to the next one. The next example on bicategories, actually this will be precisely a two category, is also easy. It is the two category of categories. So for zero cells, we take categories. Therefore, then for one cells, we take functors acting among categories, and for two cells, we take just natural transformations. So you see, this is the reason why I recalled all those categories and functors and natural transformations, just to recall how they can build this bicategory. Well, actually a two category, because one cells, which are functors, you know, when you compose functors, they compose strictly associatively and unitary. So this makes cut two, the two category of categories, and it makes it a two category rather than a bicategory, right? Because of the strict associativity on one cells. Next example has to do with tensor categories, and this is the topic of the course of Martin Mombelli. So this is a nice connection. Let us fix C to be a finite tensor category. Then for zero cells, we take C bimodule categories. For one cells, we take C linear functors, and for two cells, C natural transformations. Again, as above, C functors compose strictly associatively, so we indeed have a two category. Now, in the next example, I speak about three categories. I will not define three categories, but I couldn't resist to put you this example. First of all, let me comment this. So you see that when we define bicategories, it's like taking a one-dimension lower object, it is a one category, and then among last cells there, which are morphisms or one cells, you add morphisms among one morphisms, and these are two cells. Now in a three category, to a bicategorical structure, so to say, so to two cells, we add morphisms between two cells, and this will make a three category. This will make three cells. Three categories are much more complex to define, but let me just now tell you this example. Now, instead of fixing one tensor category C, let us choose for zero cells any tensor category. So we allow them to be C, D, E, and so on, okay? For one cells, we take C, D bimodule categories, and then guess, well, I don't know how much do you know and how quick Martin, if Martin came to that point. If you take three bimodule categories, guess, or okay, firstly, if you take two of them, what is the composition among them? Well, the composition from a CD of a CD bimodule category and the DE bimodule category will be the Deligne product over D. It is also called the relative product over D. And then if you take three of them, you can put parentheses in two ways. And there is an equivalence between these two kinds of categories. Not an isomorphism, but an equivalence. So it is a weaker relation. And this is precisely what happens in a tree category. Then for 2 cells, we take CD by module functors, and finally for 3 cells, CD by module natural transformations. So this is only to get a feeling how we can build higher categories in these examples. Okay, now I come to the graphical presentation of 2 cells, and for this I use this other slide. Now you should see it. Just tell me if you don't, but you should. Okay. Right, you see it? Graphical presentation of 2 cells. Well, I said that for every 2 objects, A and B, there is a category, B, A, B, whose objects are 1 cells and whose morphisms are 2 cells. Now, how we draw these 2 cells? Well, like this. So these A and B as objects, I put them as vertices of this bubble. I call this a bubble. And then 1 cells we write as arrows, F above and G below. And the 2 cell will be this, well, bubble, how to say, right? From F to G, and it goes from top to bottom. Okay, now here we first look at this left image below. Now this is a category, so morphisms there compose between each other. So the composition of morphisms in this category should take one kind of this alpha and then another also acting between A and B vertices. So it's here. From F to G is some alpha, and from G to H is some beta. Observe that since this is a category relying on vertices A and B, so the vertices are fixed, and I only can compose in this kind of vertical direction. So we observe that the composition inside of this category yields a vertical composition of 2 cells in the bicategory. Next information, we had this composition B functor. This is a category and Cartesian product with a category. So if we take a 2 cell alpha from here and some other beta from here, then this composition yields a 2 cell here. And let's, if we want to draw them, I draw alpha like this. Then B, observe, is the common vertex between alpha and beta. So I write beta like this. And then this whole acting from FF prime to GG prime is a 2 cell in here. So this bifunctor on these categories yields a horizontal composition of the 2 cells in the bicategory. You see these notation, this is fraction with these bullets. Well, when I draw them like this, the bubbles, and when I write equations, I write them as fractions. And here, when I write equations, I can use this notation or also this circle, well, whatever. Good. Now I come back to this slide. No, sorry, I stopped to, how do I come back to compartilhar? Okay. Yeah, you see this. Okay, this is a slide. This is I borrowed another slide, so now now we go on. And now, also related to graphical presentation of 2 cells comes the interchange law. So we have this functor or a bifunctor. The fact that this is a functor means the following. If I take 2 morphisms from the domain category and see that the domain category has pairs for arguments. So if I take 2 of them, I take 2 pairs. One is alpha beta and another is gamma delta. So the fact that this is a functor means that I may firstly compose these 2 and then act by circle, Or I can first type by circle on each of the two and then compose these two images in the codomain category. Now this I write here. So inside of the parentheses, I firstly compose alpha, beta, and gamma, delta in this domain category, and then I act by circle to end up here. And on the right-hand side, I firstly acted by this functor to alpha, beta, and I get this above, then to gamma, delta, and I get this below. And finally, I compose inside of this codomain category, which I denote by fractions. Back on the left side, the composition in the Cartesian product is defined component-wise. So here you see that this composition is given by alpha, gamma, and beta, delta, and then I act by the circle composing them. So these two should be the same. This equality is called the interchange law, and it holds strictly in a bicategory. Now, when I want to draw this with how I call them bubbles, it looks like this. So here you have alpha and then gamma, these two vertically composed, and then this whole is composed horizontally by beta and delta vertically composed. Or on the other hand, you can compose first like this horizontally and like this, and then compose vertically. So these two orders are the same. Now again, I want to make a digression with three categories because I can just not resist. In three categories, rather than having this interchange law that holds on the nose, how one says, or strictly, there is a 3-cell that controls this interchange law. That means, sorry that I switch to my other notation because this one I find very intuitive. So here I first compose horizontally alpha and beta and gamma and delta, and then at the end vertically, and here the other way around. Now the 3-cell Xi or Xi is acting as an isomorphism between these two, so the interchange law holds up to an isomorphism and not strictly. Okay, so now I want to proceed with some particular bicategory which will be of importance for us in next classes. So this is the bicategory of spans. Well, spans in C, where C is an ordinary category with pullbacks. This is again a topic that Benaboú wrote in that paper from '77. But before I introduce this bicategory, I want to recall what pullbacks are. Pullback is one particular limit in one category, so maybe many of you already know what they are, but let's just recall them. A pullback over an object B, so if you look at this diagram, then B is here. A pullback over an object B with respect to morphisms F and G, F is here below, G here on the right, is given by, well, firstly, an object P on this left above, which usually is written by X times over B, Y, this is the usual notation, and morphisms P1 like projection to the first coordinate and P2 projection to the second one, so that this identity says that this square commutes. So P1F is the same as P2G. And the next property is the universal property. I go to the next slide. Here the first point 1 is just the one from the previous slide, and the 2 is this one. For every object T like for test object, and for morphisms Q1, this is this one here, and Q2, this one here, such that this equation says that the outer diagram commutes. So Q1F and Q is equal to Q2G. For each such T and Q1 and Q2, there is a unique morphism T from the test object to the pullback such that T and then P1 is equal to Q1 and T and P2 is equal to Q2. Okay? Okay, this is the end of the definition. But I want to use this opportunity just to tell you that you can also define two categorical pullbacks, which I'm not going to define. But I want just to tell you so that you have an idea, like how does one go from one categorical to a two categorical structure? Well, if you draw diagrams that should commute in one category, passing to a two category, you require that there is a two cell which is kind of filling your diagram. So this placed in the point one, where we require that this square commutes in two categorical setting, I will require the existence of a two equivalent cell that goes from P2G to P1F, and so on for every diagram that I require to be commuted in one category, for these two triangles and for the whole one. This is just a digression because I won't like to, to let the information pass through your ears and eyes so that you get used to passing to a two categorical context. Pullbacks are unique up to unique isomorphism. This is shown easily because you can play with this T and P by interchanging the roles. If you suppose it is another pullback, then you play there and you get the uniqueness. That's the usual game. Okay, so now we can come back to define the bicategory of spans in a category C with pullbacks. So let's see, have pullbacks. Here is Benaboú, page 22, refers to Benabou's paper that is in my abstract of the course. Good. Well, let's see. Zero cells in this bicategory of spans are just objects of the category C. One cells are spans. They are just diagrams of this form. So one cells are morphisms between two zero cells. So I take two zero cells A and B. I put A and B like that in the extremes. And then one cell or this span is given actually by an additional object X and two morphisms A and B like this. Okay, so this diagram is called a span. Cross-spans have the same shape, but the morphisms go towards X. But these are spans, right? Two cells. Well, they are commutative diagrams of this form, where a two cell is acts between two one cells. So one span like this I put above, and another like that I put below. So with another X prime and another morphisms. And now the two cell is given by a morphism F that goes from X to X prime, such that these two diagrams commute. So A should be equal to FA prime, and here the same. You can also draw these as two triangles, but drawing them as squares has the advantage of facilitating the passage to double categories. So there is also a double category spans, but this is just a digression. And now I want also to tell you, before going to vertical composition of two cells, how you put the identity one cell on a zero cell. On a zero cell A, you would have A here and A here, and then identity one cell would be given by putting just the same A here and identity on A in place of these A and B. Now, vertical composition of two cells is easy. It's just vertical juxtaposition of these kind of diagrams. What is more complicated is the horizontal composition of one cells and the two cells. So we have to start with the one cells. Two one cells or spans which are composable are here. We have this one AXB, and then here it ends with B, and the next one starts with B. The next one is this that goes to Y and then C. So these two we will compose by using the pullback, and this C has pullbacks. So the pullback of these two arrows B2 and B1 is given by this object here with two projections, so that we have this rhomb right here above that commutes. And so for the composition of these two spans for one cells, I will take this above one, this hole that I'm showing now. that means that there is this object, this projection followed by A, and this other projection followed by C. And now I'm going to show you how we define composition of two cells. Remember from the previous slide that the two-cell is diagram of this form. So here, one two-cell is this one, given by F, acting between X and X prime, and another one is here, and it acts by where G acts from Y to Y prime. So then the composition of these two spans is given by the above one, by this pullback above, and the composition of these two below spans is given by this span here, X prime times Y prime, and the whole composition is here. Now, the two-cell, the resulting two-cell will be given by the whole this here, H in the middle, and then whole this here. So first I need to tell you how I get this H. Well, I get it from the pullback property. I use the fact that this is pullback, and I use this upper object as my test object. Then I need to give two morphisms. One is Q1, going from here to here. So for that Q1, I take this composition P1 and F. And the other one, Q2, is this one, going from P2, it's P2 followed by G. Now I need to show if this and then followed by B2 prime is the same as this and that's then B1 prime. Let's check it here below in the equations. So let's start from here. And then I use that this square here commutes because of these two cells that I had from the beginning. So I say because of X. So then this F followed by B2 prime is the same as this B2, and here is just identity. So I came here. Then I end up in B2, P1. But now, since this above is a pullback, so this is a pullback, I know that this composition is the same as this one. And this is this equation here, P2 and then B1. Now again, but because of this square here, and I know that it commutes because of the second two cell, I know that B1 is equal as G B1 prime, and that brings me here. So in the end, I proved that this here is the same as this here, and then by the pullback property, I have the existence of this H, and it is such that H and then P1 prime is the same as P1F, and the same here. So these back squares, mostly lila, commute. And since this square here commutes from the beginning and this one too, then I get that the whole rectangular here commutes and also the whole one here, and then it gives me a proper two-cell in the bicategory of spans. Right? So the two cells were given so that you give this H so that these commute, and we got it. We just got it here. Okay, and now associativity and left and right unity natural isomorphisms, alpha, lambda, and rho for this bicategory are given by the usual respective isomorphisms for the pullbacks. So there is not much more to say. So that is this bicategory of spans. And well, for the time being, we leave it here. We leave this bicategory at this place. That was another example of a bicategory, and we will come back to it later. Now, in the next part of the talk, I go towards higher categories of bicategories. That is, firstly, let's see like functors among bicategories. Well, we saw that categories, which can be also called one categories, organize into a two category of categories. You take for zero cells categories, there for one cells functors, and for two cells natural transformations. But they also organize into just an ordinary category. You take categories and functors. Since the functors compose strictly associatively, you already have a category, and you can stop there. Now we will see how bicategories organize into a three category that I will denote by Bcat3, but they also organize into a 2 category, which I will denote by Bcat2. Okay, so these are like just titles, and now we go to define some things. Well, pseudofunctors. Among bicategories, there are pseudofunctors, f from B to B prime. They consist of, again, an assignment that to an object assigns an object in the codomain bicategory. But now for every 2 fixed objects, there is a functor of this form. This is similar to functors among categories, but now we require this to be a functor, so it has more properties. And additionally to this functor property, we require that for each 2 composable 1 cells F and G, there are natural isomorphism 2 cells. One is Xi and another is theta. Well, Xi is this isomorphism controlling this compatibility of F with the composition, and theta is an isomorphism that controls this compatibility of F with the identity on object. And now these Xi and theta are required to obey a hexagon and 2 squares on this slide. Well, I didn't define here monoidal functors, but if you recall their definition, you will see that this is the precisely the same hexagon and 2 squares, where just instead of objects, now we take 1 cells. So there is nothing really new, special happening here. Now, the fact that we have these functors, it means that, okay, first for objects, for every 1 cell, you get another cell in the codomain bicategory. The same for the 2 cells, but then the functor has this property that it strictly obeys the composition on morphisms, which here are 2 cells. And the composition of 2 cells in these categories, this one and this one, is given by vertical composition of 2 cells. Okay, so here is one example of a pseudofunctor, and it is again related to tensor categories and the course of Martin. Recall that I gave you this example of the category of C bimodule categories. I didn't write this name C bimod, but I say you now. So 0 cells were C bimodule categories, then we had for 1 cell C module functors, and finally C natural transformations. Any CD bimodule category M, so C on the left, D module category on the right, gives rise to a pseudofunctor, where this is tensor, the Deligne tensor product over D, from the category of left D module categories to C module categories. So this is why to end up in C mod, we require that M is the left C module category. How it acts? If I take any D module category from here, then M tensor Deligne with N gives me this other C module category. If I take a functor, then this tensoring with F gives me another functor where this first coordinate acts as identity on M, and then just F is acting on the right. And similarly for D module natural transformations, M tensor alpha, on the left we have identity, and alpha acts on the right. I also wrote it here. So if you take an object living in this category here, M tensor alpha, which is a natural transformation, it is being evaluated here. It is like this. And then you just act as identity on the left, and alpha is acting as a morphism on the right. The natural isomorphism that controls the compatibility of this pseudofunctor with the composition of 1 cells, that is with the functors, C module functors, is given by an isomorphism. So M tensor, this composition, is not equal, it is isomorphic to this composition of these 2 functors. Well, actually, there are 2 two interpretations of the Deligne product, Deligne tensor product, like two schools, or how to say, two groups of researchers. So some consider this being identity and some not, but an isomorphism. Like strict Deligne original definition would mean that this is an isomorphism and not strict identity. So then this is an example for a pseudofunctor. And finally, pseudo-natural transformations. Among pseudofunctors, there are pseudo-natural transformations. This is like omega, which I denoted by omega for categories. Now I denote it by chi. It consists of families of one cells. This part of information is precisely the same as for usual natural transformation, but we have some additional data that we require here, and that is that for every one cell F from A to B in the domain category, there is an isomorphism to cell natural in F, that is that chi F. Well, you will understand better if I draw you this square. So if this chi F would be just an identity, then you would have a commutative square which defines a common natural transformation. But since here we have two cells, then this chi F is required to be an isomorphism to cell that acts from this one cell towards this other one cell, or the other way around, that is isomorphism. And of course, every time when in a higher categories you require existence of an isomorphism, you need to say up to which axiom. So which axioms it has to obey. Well, here the axioms, there are two axioms. You don't have to bother recalling what they are. It's just important that you notice that they give you compatibility of that two-cell chi F with a composition of one cells. So in the previous slide, recall that this two cell is given for every one cell F. And now here observe that we give a compatibility of this chi with a composition of two one cells G and F. And here you have chi for G and chi for F. And then these coherence for the functor G and coherence for the functor F. And the second axiom gives me compatibility of this two-cell chi with the identity one cell. And here are used left and right unity constraints, and this theta, theta for the coherence for the functor G and F. I mean, it's not so important to remember, but it's just to get a feeling of how things complicate when you go to a higher categorical level. Now, among pseudo-natural transformations, there are also modifications, but I will not define them. And I already can tell you that there is a tree category, which I denote by Bicat3, which has for 0 cells bicategories, for 1 cell pseudofunctors, for 2 cells pseudo-natural transformations, and for 3 cells these modifications. Sorry. Okay, so now let me tell you this. When you work with higher categories, always when you go to a higher category, a higher dimension, you see that the axioms complicate. There are more axioms, and it is more complicated to verify the laws. So one wants, if one already works with some complex categorical structures, one tries to be able to describe it with lower dimension. So instead of working with the tree category of bicategories, Steve Leck found a way how to get a 2 category of bicategories. So in Steve Leck, Icons is the title of the paper from 2007. He introduces icons. This is instead of pseudo-natural transformation, so this is an alternative for the 2 cells here. They are introduced as identity, component, oplex, natural transformation. This means that instead of pseudo-natural transformations, where theta and psi, where this chi should be isomorphism, So instead of having an isomorphism, oplex means that we require the specific cell in a one direction, and then this identity component means that these one cells chi A are identities. Okay, that's just some restriction. So from pseudonatural, you first generalize to oplex, and then you restrict to just identity component oplex natural transformation, whatever. It's just important that you see that there is some other gadget called icons. This icons is actually taken from like acronym, sigla, identity component oplex natural transformation, icon, right? And well, Steve Leck proved that this yields a two category as follows, that I denote by bcat2. On zero cells are bicategories, but now for one cells, one needs to go to lax functors, not pseudo, but lax functors. And for two cells, you take icons. Well, then you have a two category of bicategories. So this was about these higher categorical structures on the bicategories. Well, it seems that no. So now would be the end, but I also started a little bit late. There is only one slide more, and this is about stratification theorems. Somewhere before I mentioned that in a monoidal category, we had these alpha, lambda, and rho natural isomorphisms. If they are identities, then your monoidal category is called strict monoidal. One example of such a category is the category of endofunctors on any category C. Why this is monoidal at first? Well, the composition here is given just by the composition of functors. I mean, this category has for objects functors and for morphisms natural transformations. Okay. Why is this monoidal? On objects, which are functors, the tensor product is given by the composition, and the unity is identity functor on C. And why is it strictly monoidal? Because this composition of functors is strictly associative and unital. When in a bicategory, alpha, lambda, and rho, the analogous ones, are identities, then we have a two category. We also said this. And now in a three category, which I didn't define, but I told you that there are, at many levels, you require some existence of isomorphism cells. So you can consider different types of three categories depending on at which level you consider isomorphisms and where identities. So now, one specific tree category where everything is strictly identity of these coherent cells, but the interchange law is an isomorphism, such a tree category is called a gray category. And the stratification theorem that I will cite in a moment will tell you that this is the strictest tree category possible. So we have stratification theorems in different contexts. Each monoidal category is equivalent to a strict monoidal category. This, I guess, everybody here knows. Now, each bicategory is B-equivalent to a two category. This should not surprise you. This exists. Each three category is three equivalent to a gray category. In this sense, there is nothing more strict, nothing stricter than gray category. So the interchange law really has to be up to an isomorphism in any three category. And the last line is about pseudo double categories, which I will define in the next talk tomorrow. But just because the topic is stratification theorems, I will tell you now, each pseudo double category is double equivalent to a double category. So we have these stratification theorems, and this will end my talk. I was only seeing my slide and I didn't see anybody else. I didn't hear anybody and any question, and I hope that you could hear it well, that you could follow well. And now I would ask you if there are some questions. So tomorrow we will.
I think we see tomorrow. Thank you, Bojana.
Okay. Thank you for your attention.
Thank you.